Okay, so now let's continue with organic chemistry. Now, today we will not finish everything. We just do the introduction to organic chem. So we will go through what organic chem is and some of the common homologous series that you might see at O level and A level. Okay, so let's start. So what is organic chemistry? Organic chemistry basically is a study of compounds of carbon. So carbon-containing compounds are called organic compounds. So this word organic is related to carbon, but not all carbon compounds are organic. The exceptions are CO2 and carbonates. So like calcium carbonate is not considered an organic compound. All right. Is there a reason behind this? No. All right. It's just how the discipline has evolved. All right. And this is where I want to talk a little bit about history. Very often, many students will complain that organic chemistry seems very different from the rest of the chemistry that you have learned previously. But there's a reason for this. Organic chemistry did not come from chemistry. Organic chemistry came from the study of biology, life sciences. So most organic chemists actually were previously from biology. Why is that the case? This is the case because most organic compounds, including the first two that I've shown here, are obtained from living things. So these compounds were isolated from living things by studying humans, mammals, and so on. All right. So organic chemistry tends to use different terminology, different lingo for the same thing, as we will see very shortly. All right. And that's the reason why CO2 and carbonates are not considered organic. Is because carbonates were studied as part of another field of chemistry. All right. So like calcium carbonate, they study as part of another field of chemistry. That's why it's not considered organic. Okay. Now, why carbon so specifically? Now, if you look at these two molecules, they kind of look similar, right? In fact, they are very similar. There are only a few differences. So let's look at the similarities first. Do you realize, oh my god, these rings like look exactly the same? Well, almost the same. Whatever I've highlighted in yellow looks almost the same, right? Indeed, they look really, really similar. The differences, notably, here there's a C double bond O, whereas here there's a OH. Okay, now these have names. The C double bond O here is called a ketone, whereas the OH here is called alcohol. And here comes the first difference between organic chem and the rest of chem. Organic chem calls OH alcohol or hydroxyl group, whereas in other parts of chemistry, the OH would have been called hydroxide. So obviously, that's the first difference. We use different terms. Organic chemistry will use different terms from the rest of chemistry. Now, the next thing is you realize, hey, it's just one difference, right? Like 90% of the molecule still looks fairly similar. But can you see? These are two radically different molecules. The one on the left is called testosterone, which of course is the male sex hormone in humans. Whereas the one on the right is estrogen, the female sex hormones in humans. And this is the difference between male and female. All right? Can? And the difference between male and female is simply because one has a ketone, the other one has an alcohol at their place. All right? Can? So HO and OH are the same. All right? It's just that C is covalently bonded to O. That's why we draw HO. Is to represent that O is covalently bonded to C. All right? So HO and OH are actually the same. It's just that over here we call it an alcohol because it's organic chemistry. All right. So I hope you can see just a slight change in the groups has resulted in a huge change to the final outcome, right? Male versus female. Okay. Even though the rings look quite similar, it has resulted in a huge change. And that is the beauty of organic chem. Organic chemistry is so wonderful simply because a small change to the groups results in a huge change to its reactions, to its properties. Okay. And that's why organic chem is a vast field of study. Changing one single thing results in a huge change to everything else. All right. So of course we won't finish all the properties of organic chemicals, but as you go on and study more and more chemistry, you realize that oh my god, even just changing one atom or even just changing the position of the atoms. Let's say if the OH wasn't there, if the OH was like on a different carbon atom, it makes a huge difference to your life. All right. Okay. Now, but why carbon? Let's go through why carbon first. Now, I'm not sure if the SJChO have gone through this. Why carbon so special? So let's think about carbon. What do you know about carbon? Carbon got 6 electron, 2, comma 4, right? That's the electronic configuration of carbon. Now, if you recall our lesson about SPDF, we can rewrite this as 1s2, 2s2, 2p2. All right, it's the same thing. So the electronic configuration of carbon shows you that it has 4 valence electrons. If it has 4 valence electrons, it needs 4 more valence electrons to achieve a fully filled outermost shell, meaning it forms 4 bonds. Carbon always forms 4 bonds. If you can find a molecule in which carbon can form something less than 4 bonds, you will win the Nobel Prize. All right? It's how extreme it is. Carbon always forms 4 bonds in a stable molecule. Can you force carbon to form just 2 bonds? You could, but the molecule is unstable. If you are able to make a stable molecule where carbon has anything less than 4 bonds, you will win the Nobel Prize. It's how difficult it is. So if you notice that you can go and count later testosterone, estrogen. If you just look at carbon and count, there's 4 bonds around it. Confirm there's 4 bonds around the carbon. All right? Can? 4 bonds is a lot. If you think about it, like other elements like hydrogen forms only 1 bond. Oxygen forms 2 bonds. Carbon forming 4 bonds is a big deal. Because it has so many bonds to form, it can form long chains. But instead of forming long chains, how about forming cyclic rings? Not just chains, right? It could form rings. So when we say rings is a network, it can network. All right. Moreover, carbon-carbon covalent bonds are strong. All right. So the molecules that it forms will be stable. Okay. Now, so that's carbon. We focus on carbon first. Can carbon form more than 4 bonds? No, also cannot. If you can do that, you will win the Nobel Prize. But it's not allowed. Because to form more than 4 bonds, carbon will need to use the inner shell electron, which is not allowed. So isotopes also will not form more than 4 bonds, because isotopes have the same number of protons and electrons, right? So the isotopes of carbon also will be 2, 4. It will not, because of isotope, then it forms more bonds. No. Isotopes have the same number of electrons, right? Okay? No, it's not allowed because you can't use the inner shell. Inner shell too much energy. It's not allowed. Even with energy, it's not gonna do it. Okay? Now moving on. Now, organic compounds, sadly, is a vast field of study. This is like 10% of organic chemistry. There are 4 different families of organic compounds: alkanes, alkenes, alcohols, and carboxylic acids. So the SecFors already know this. All right. So there are 4 different families, but actually there are many more. So why do we group them into families? So if you think about it, okay, the rest of chemistry, we group everything according to groups and period. Organic chemistry, you don't do that. Because organic chemistry is more meaningful to study them as a family of compounds. So the first family is called alkanes. Now, the alkanes have a general formula of CnH2n plus 2. General formula means this formula is obeyed by all members of the alkane family. The alkane homologous series, every alkane will obey this formula, CnH2n plus 2. So what on earth is N? N in organic chemistry is the number of carbon atoms. So if the alkane has 1 carbon, N is equals to 1. If the alkane has 50 carbons, then N equals to 50. All right. So I'll demonstrate for you. This alkane has 2 carbons. So N equals to 2. So C2H, 2 times 2 plus 2. So it's C2H6. Which makes sense. Okay, you can see the C2H6. Okay, there are 6 hydrogens. So different families will have different general formula. Same family, same general formula. All right. So that's C2H6. So you can see next one, alkene, CnH2n. Different formula already. Alcohol, CnH2n plus 1, OH. Finally, carboxylic acid, Cn minus 1, H2n minus 1, COOH. What on earth? Why will they be different? They are different in terms of general formula because different families have different bonds, different atoms inside it. So now we move on to the next concept. Alkenes have a different formula from alkane. That's because they have a carbon-carbon double bond. So the carbon-carbon double bond is present only in alkenes, but not alkanes. So this is a carbon-carbon double bond. So alkenes have this. Now a double bond is two bonds. So if you count the number of bonds, one, two bonds are. So around each carbon, the rule is you must always have four bonds. So one, two here already. Three, four. That's why you can see an alkene has fewer hydrogens than alkanes. Because the double bond already took up some of the bonds of carbon. So how many more hydrogens could each carbon bond do? Fewer. Because ultimately, every carbon must only have four bonds and nothing more. Four is the only number allowed. And hence, CnH2n. You can see the H is lower in number. Previously, it was 2n plus 2 for alkane. But now you got fewer hydrogens because of the double bond. Hence, the formula is C2H4. Because two carbons, therefore four hydrogens. 2 times 2, 2n. Okay? Now, the carbon-carbon double bond is special. Whenever you see a carbon-carbon double bond, we say the molecule or the compound is unsaturated. Unsaturated means there is a carbon-carbon double bond present in the molecule. So alkenes are unsaturated. Now, it must be a carbon-carbon double bond. Cannot be some other double bond. Must be carbon-carbon double bond. Now, this word unsaturated again comes from biology. Okay? In other parts of chemistry, saturated means something else, right? So you got to learn in crystallization, heat the solution until it's saturated. That is a different meaning. This unsaturated means there is a carbon-carbon double bond, and it came from biology. So those pure bio students will know. You would have done the heart, for example. Then you would have learned that, oh, you cannot eat so much saturated fat because saturated fat will clog up your blood vessels. It will block your blood vessels, prevent blood flow, blood transport of oxygen to other parts of the body, right? So saturated means there is no carbon-carbon double bond. If there's no carbon-carbon double bond, it's saturated. So alkanes are saturated, alkenes are unsaturated. So cannot eat so much saturated fat. Saturated fat, by the way, is alkane. All right. Cannot eat so much of that. You must eat more unsaturated fats because unsaturated fats tend not to clog up the blood vessels, especially those in the heart. Okay. So I hope this links with biology. So now it gives you more context why Miss Bo might keep saying unsaturated fats, unsaturated fats, saturated fat. So the meaning of unsaturated is there is carbon-carbon double bond present. Okay. Now next we move to alcohols. Alcohols have a rather quirky general formula CnH2n plus 1 OH. What? What? Why must you put the OH at the end? Why couldn't you just put the H together with the H2n plus 1? The idea is When we leave the OH at the end like this, there's a reason. It's because we want to show the reader that there's OH group at the end. Now, the OH group is called the hydroxyl group. Like I said, in other parts of chemistry, OH is called hydroxide, but now it's organic. Organic chem, we are going to call it hydroxyl group. The hydroxyl group is the group present in alcohols. So whenever you see OH in organic chemistry, it's alcohol. All right. And finally, the last one is carboxylic acids. Carboxylic acids, okay, have a rather strange formula, Cn minus 1 or minus 1, H2n minus 1, COOH. So again, why do you bother writing COOH at the end? It's because you really want to demonstrate to the reader that this is the group, COOH. So what is COOH? COOH consists of C double bond O, single bond O, single bond H. So you need to know COOH has a double bond to O, single bond to OH. Now, this is also given a name. It's called a carboxyl group. And that's why it's called carboxylic acids. And you have learned this before. So the three flourish, you just got tested this in WA2. This is CH3COOH, which is ethanoic acid. So three flourish, the question about weak acid, I tested you on this, right? Ethanoic acid is CH3COOH. Haven't you wondered why on earth don't put all the carbon together? Why must write CH3 then COOH again? Now you know. You need to write the COOH at the end because that is the group that you must show the reader that is present. Okay? Now, how did I arrive at CH3COOH? There's two carbon. N equals to 2. So you sub in N equals to 2. So N equals to 2. So N is C, N minus 1. So C2 minus 1. H, 2 times 2 minus 1. Then COOH. So you get CH3, COOH. All right. So now you can see more logic. Why on earth would you put the COOH at the end for organic acids? Because organic acids are carboxylic acids. So you must put the COOH at the very end. Okay. Now, carboxylic acids are acids. They are weak acids, but they are still acids. So they will react with metals. They will react with base. They will react with carbonates. All right. So if you recall, ethanoic acid could react with sodium. It could react with sodium hydroxide. It could also react with sodium carbonate, just like any acid would. All right. Now, I've gone through a lot. Now, importantly, you need to realize a few things. Every homologous series, every family has its own general formula. The general formula is the one with N inside it. The N is the number of carbon atoms. Okay. The second thing you need to realize is, okay, different families, different general formula. Besides that, different families, different bonds, different atoms. Now, these bonds that I've highlighted in yellow, they are called the functional group. Meaning, if I see carbon-carbon double bond, I know that's the functional group of alkene. I know that's going to be an alkene. If I see OH, that's going to be alcohol. If I see COOH, it's going to be a carboxylic acid. From the functional group, you literally can tell what homologous series, how it's going to react. For example, I gave you an example just now. If I see COOH, it's an acid. It's going to react with metal. It's going to react with base. It's going to react with carbonates. All right. Ken? Now, are these the only families, only homologous series in organic chem? No. This is the reason why when you reach A level, some of you went to JPJC, you saw the JC2 students were doing nitrogen compounds. There are a lot of other homologous series involving nitrogen. So over here at O level, we restricted it to just these 4. But I'm going to introduce more probably tomorrow's training. We're going to look at more homologous series. Okay, but before we move on, okay, do you need to know the general formula? Yes. Would you need to know functional groups such as OH is alcohol, COOH is carboxylic acid, carbon-carbon double bond is alkene? Would you need to know that? Yes. All right. And finally, let's end off today with this. More terminologies. Hydrocarbons. What is a hydrocarbon? As the name suggests, hydrocarbons are organic compounds that contain hydrogen, so the hydro refers to hydrogen, and carbon atoms only. Only is very important. That means in the compound there can only be H and C. Cannot have O, cannot have N, cannot have Cl. All right, can only be H and C. So if you look at it, only alkanes and alkenes will be hydrocarbons because only alkanes and alkenes have H and C only. Okay? Now you will hear this word hydrocarbon a lot. All right? For instance, you may hear unsaturated hydrocarbon. So unsaturated hydrocarbon is what? Unsaturated hydrocarbon means, okay, this compound only has H and C and it has a carbon-carbon double bond because unsaturated. Okay, so this page has a lot of detail. I hope you would internalize this. Okay, next, we talk about family a lot. The family is called homologous series. So homologous series is a family of organic compounds with the same general formula, similar chemical properties. That means they will react the same way. So all alkenes react similarly, they undergo similar reactions. But what is this due to? It is due to the same functional group. So we'll go through what a functional group is. Next, we have gradual trends in physical properties. Don't worry too much about this. We'll go through this tomorrow. All right, some of the physical properties. All right, and okay, the molecular and structural formula differ from next member by CH2 group. Don't worry about this. We'll go through this tomorrow as well. More importantly, you need to know what's general formula right now. You need to know what's functional group right now. Okay, so we're going to go on the functional group. So just now we mentioned OH, alcohol, COOH, carboxylic acid. So those are functional groups. You see the group, you know it's an alcohol. You know it's a carboxylic acid. So basically, a functional group is an atom, one atom, or a group of atoms like OH, COOH is a group, right? That gives the homologous series its characteristic chemical properties. Okay? So like OH, alcohol, therefore, that is gonna react like alcohols. COOH, carboxylic acid, so it's gonna react like carboxylic acids. Which brings me back to WA2 for three flourish again. Ethanoic acid has so many hydrogens, but why only one hydrogen is dissociated? Why? Of so many hydrogens, why only one hydrogen can be dissociated in ethanoic acid? And now you realize why. Because it's the idea of functional group. The functional group of ethanoic acid is the COOH. That means only that group reacts. The rest of the molecule doesn't react. Hence, if only the COOH can react, effectively speaking, only the hydrogen in COOH could dissociate out. And that's why ethanoic acid only gives you one H plus when dissociated. Okay? So that links whatever we did in WA2, acids and bases, with organic chemistry now. Now that you know the functional group COOH only got one H that can dissociate out. So only the functional group is the reactive part. The rest of the molecule is actually not reactive at all. All right? Now, I know this is going to be very boring for the Sec 4s, but let's revise. How do we name and draw organic compounds? Now, there's a system to this. For example, if the name is ethane, okay, the first part is called the prefix. The prefix tells you the number of carbon atoms. All right? So if the name starts with F, then got 2 carbon atoms. Meth 1. So you might have heard of methamphetamine. Methamphetamine is a drug. The word meth means there's somewhere in the molecule there is a meth group, which is 1 carbon. All right. So meth 1 carbon, F 2 carbon, prop 3 carbon, bute 4 carbon. So the first 4 are hard to learn. Meth, F, prop, bute. 1 carbon, 2 carbon, 3 carbon, 4 carbon. So the first 4 must be learned, and it's hard to deduce. But after 4 carbon atoms, the next ones are very easy to learn. Pent is 5. Pentagon, 5 sides. Pent means 5 carbon in this case. Hexagon, 6 sides. So hex means 6 carbons. And so on, so forth. Okay? So the first part, the prefix will tell you the number of carbons inside the molecule. Now, when I say number of carbons, I mean the total number of carbons. Okay? Now, ane. Ane, the second part of the name, tells you which homologous series it belongs to. Alkane, so ends with ane. All right, so in this case, ethane, eth means got 2 carbon, is an alkane. So how to draw? Mr. So will start with the 2 carbons. I will put them in one line. It's an alkane. Do alkanes have double bond? Do alkanes have OH? Do alkanes have COOH? So you got to remember, alkane don't have double bond. Alkane don't have OH. Alkane also don't have COOH. So it's just a single bond. Very plain, very old, very simple. All right. Now, the next part is carbon atom must always form 4 bonds. Please make sure there are 4 bonds around each carbon atom. So once you have arranged 4 bonds around each carbon atom, the rest are just filled with hydrogens. Okay, so that's ethane. The structural formula of ethane is as such. Okay, it's C2H6. Next, okay, we can try drawing propane yourself later. Let's not draw propane. Let's go to butene. Okay, so go to page 6, part 4, butene. So but means what? So let's analyze the name. But means got 4 carbon. Ene means what? The second part of the name, sorry, is ene. Ene means alkene. So alkene means there is a double bond. Okay? Now, alkenes have a double bond between carbon atoms. Carbon, carbon, double bond. But how many double bonds are there? There's only one. That means the rest are single bonds. Very simple, very old, simple, single bonds. Okay? Lastly, every carbon atom must form 4 bonds. Please count. The double bond is already 2 bonds, so you can only have 2 more. Next, the next carbon atom, there's a double bond, there's a single bond, 3 bond already. So you are only allowed 1 more bond to make 4, right? 3 plus 1 equals 4. Okay? So this is butene. Now, this is one way to draw butene. There is another way to draw butene. All right? There is another way to draw this particular compound. All right? And I will stop here. So your homework is to try drawing everything on page 6. Part 1, 2, 3 should be quite straightforward. And to do part 4, I have shown you one way of drawing butene. What is the other? For the Sec 4s, you already know this, but for the Sec 2 and Sec 3, you don't. I want you to try. What could be another way to draw butene? All right. And I will stop here for today. This is homework. So let me just stop the recording now before I answer the questions.